Welcome to OSPF Mastery. Welcome to the channel. Please consider subscribing. I produce videos daily covering a wide variety of cloud topics with focus on networking. Also, hit the bell icon to get notified of new videos. Today, we're diving deep into OSPF, the Open Shortest Path First Protocol. If you've ever struggled to remember the different LSA types, area types, or route types in OSPF, you're in the right place. I'm going to share memory techniques that have helped thousands of network engineers master these concepts. OSPF can seem overwhelming at first with its 7 LSA types, multiple area configurations, and various route types. But here is the secret. Once you understand the patterns and use the right memory tricks, it all falls into place. By the end of this presentation, you will have a complete mental framework for OSPF that you will never forget. We'll start with the fundamentals of OSPF, then dive into each LSA type with real-world examples. I'll show you exactly how to remember all 7 types using a simple mnemonic device. Then we'll explore OSPF areas and finally tackle those confusing E1, E2, N1, and N2 routes. Let's begin. OSPF Fundamentals. Before we dive into LSA types, let's quickly review what OSPF is and why it matters. OSPF is a link state routing protocol, which means routers share information about the state of their links with all other routers in the area. This is fundamentally different from distance vector protocols like RIP. The genius of OSPF lies in its hierarchical design. Instead of every router knowing about every single link in your entire network, OSPF uses areas to create boundaries. Area 0, the backbone area, is at the center, and all other areas must connect to it. This hierarchy is what makes OSPF scalable to massive networks. Link state advertisements, or LSAs, are the building blocks of OSPF. Think of LSAs as different types of messages that routers use to share topology information. Each LSA type serves a specific purpose, and understanding these purposes is key to mastering OSPF. The Link State Database, or LSDB, is where all these LSAs are stored. Every router in an area has an identical LSDB for that area. When troubleshooting OSPF, checking the LSDB is often your first step. The command show IP OSPF database will become your best friend. Finally, OSPF uses the Dijkstra algorithm to calculate the shortest path to each destination. This calculation happens independently on each router, using the information in the LSDB. The result is a loop-free topology with optimal paths. The 7 LSA types overview. Now, let's tackle the heart of OSPF, the 7 LSA types. I am going to share with you the mnemonic that changed everything for me. Really nice students study some advanced networking. Each word represents an LSA type, and I will explain why this works so well. LSA type 1 is the router LSA. Really, every single router generates type 1 LSAs. These describe all the router's links within an area. If you have 10 routers in an area, you will have 10 type 1 LSAs. They stay within the area and never cross area boundaries. LSA type 2 is the network LSA. Only designated routers, or DRs, on multi-access networks generate these. Imagine Ethernet segments where multiple routers connect. The DR creates a type 2 LSA to represent that shared segment. No DR means no type 2 LSAs. LSA type 3 is the summary LSA students. These are created by area border routers, ABRs, to advertise networks from one area into another. Despite the name summary, they do not actually summarize by default. They advertise individual networks between areas. The remaining types, 4, 5, and 7, deal with external routes and special area types. Type 4 helps routers find ASBRS, Type 5 carries external routes, and Type 7 is used in not-so-stubby areas. We will explore each in detail, but first, let me show you this visual representation that makes it all clear. LSA Types 1 and 2, Router and Network LSAs. Let's dive deep into Type 1 router LSAs. Every router, without exception, generates a Type 1 LSA for each area it's connected to. This LSA contains all the router's interfaces in that area, their costs, and what they're connected to. It's like the router's autobiography for that specific area. Here is a crucial point. Type 1 LSAs never leave their area. They are flooded throughout the area but stop at ABRs. This is fundamental to OSPF's scalability. Imagine if every route knew about every link in a 10,000 route network. The LSDB would be enormous. The show command, show IP OSPF database router, displays all Type 1 LSAs. You will see the advertising router's ID and all its links. Each link shows whether it is a point-to-point link, a transit network, a stub network, or a virtual link. Understanding these link types is crucial for troubleshooting. Type 2 network LSAs are fascinating because they exist only on multi-access networks that have a DR. The DR creates this LSA to represent the entire segment as a pseudonode. Without Type 2 LSAs, every router would need to maintain adjacencies with every other router on the segment. This would be a full mesh nightmare. The Type 2 LSA lists all routers attached to the segment. When you see a Type 2 LSA in the database, you know there is a multi-access network with multiple OSPF routers. The command show IP OSPF database network reveals these LSAs and which routers are on each segment. LSA Type 3 Summary LSAs. Type 3 Summary LSAs are perhaps the most important LSAs for inter-area routing. Despite their name, they do not perform route summarization by default. That is a common misconception. Instead, they advertise individual networks from one area to another. Only ABRs generate Type 3 LSAs. When an ABR learns about a network in one area, from Type 1 and 2 LSAs, it creates a Type 3 LSA to advertise that network into other areas. Think of ABRs as translators between areas. They speak the language of multiple areas and translate between them. Here is where it gets interesting. Type 3 LSAs are regenerated at each ABR when a Type 3 LSA reaches another ABR. That ABR does not just pass it along. Instead, it creates a new Type 3 LSA with itself as the advertising router. This regeneration is why the advertising router in a Type 3 LSA is always an ABR in your local area. The metric in a Type 3 LSA represents the cost from the advertising ABR to the destination network. Routers add their cost to reach the ABR to calculate the total metric. This is why having optimal ABR placement is crucial for good OSPF design. You can view Type 3 LSAs with Show IP OSPF Database Summary. You'll see networks from other areas and which ABR is advertising them. If you have multiple ABRs, you might see the same network advertised by different ABRs with different metrics. OSPF will choose the best path. LSA Types 4 and 5 ASBR Summary and External LSAs. Type 4 ASBR Summary LSAs have one job: to help routers find ASBRs in other areas. When an ASBR exists in an area, the ABRs connected to that area generate Type 4 LSAs. These LSAs tell routers in other areas how to reach that ASBR. Without Type 4 LSAs, routers would not know how to reach external routes advertised by distant ASBRs. Think of Type 4 LSAs as street signs pointing to the ASBR. They do not carry route information themselves. They just say, to reach ASBR with router ID X.X.X.X, come through me with this cost. This elegant solution allows OSPF to scale external route advertisement across multiple areas. Type 5 external LSAs carry routes from outside the OSPF domain. Only ASBRs generate Type 5 LSAs, typically when redistributing from another routing protocol, static routes, or connected interfaces. These LSAs flood throughout the entire OSPF domain unless blocked by stub areas. Here is where E1 and E2 routes come in. Type 5 LSAs can advertise external routes as either E1 or E2. E2 routes, the default, maintain a fixed metric regardless of internal OSPF costs. E1 routes add internal OSPF costs to the external metric. We will explore this distinction in detail later. The command show IP OSPF database external shows all Type 5 LSAs. You will see the advertising ASBR, the external network, and whether it is E1 or E2. In large networks, controlling Type 5 LSA propagation through stub areas becomes critical for scalability. LSA Type 7 NSSA External LSAs. Type 7 NSSA external LSAs are special because they only exist in not-so-stubby areas, or NSSAs. NSSAs are a brilliant compromise. They block Type 5 LSAs like stub areas but still allow local route redistribution through Type 7 LSAs. Here is the key insight. Type 7 LSAs are almost identical to Type 5 LSAs in content, but they have a different flooding scope. While Type 5 LSAs flood everywhere, Type 7 LSAs stay within their NSSA. This containment is what makes NSSAs so useful. The magic happens at the ABR when a Type 7 LSA reaches an NSSA ABR. The ABR translates it into a Type 5 LSA for advertisement into Area 0 and beyond. This translation is automatic and seamless. The P-bit in the Type 7 LSA controls whether this translation occurs. In practice, NSSAs are ideal for branch offices that need to advertise local routes, for example, a local server or voice gateway, but do not need to receive the full routing table. They provide the benefits of a stub area with the flexibility to originate routes locally. The command, show IP OSPF database NSSA external, displays Type 7 LSAs. You will only see these in NSSAs. Pay attention to the P-bit and forwarding address. These determine how the route will be translated and used. Understanding Type 7 to Type 5 translation is crucial for NSSA design. OSPF area types. Now let's explore OSPF area types. Understanding these is crucial because they control which LSA types are allowed, directly impacting routing table size and convergence speed. I'll share memory tricks for each type. First, the standard area. This is your default. It allows all LSA types and has no special restrictions. Every OSPF network has at least one standard area. Area 0, the backbone. Think of standard areas as anything-goes areas. They are flexible, but can lead to large routing tables in big networks. Stub areas are where things get interesting. They block Type 5 external LSAs and use a default route instead. The logic is simple. Why does a branch office need to know about every external route when all traffic goes through the head office anyway? Stub areas reduce memory and CPU usage on smaller routers. Totally stubby areas take this concept further. They block both Type 5 external LSAs and Type 3 summary LSAs. Only routes within the area and a default route remain. This is Cisco proprietary but widely supported. It's perfect for areas with one exit point. Not so stubby areas, NSSAs, are the Swiss Army knife of OSPF areas. They block Type 5 LSAs like stub areas but allow local external route origination through Type 7 LSAs. Totally NSSAs combine NSSA functionality with totally stubby behavior. Let me show you when to use each type. E1 versus E2 routes. The distinction between E1 and E2 external routes is one of the most misunderstood aspects of OSPF. Let me clear this up once and for all. The key difference is how OSPF calculates the metric to reach these external destinations. E2 routes, the default, maintain a fixed metric regardless of where you are in the OSPF network. If an ASBR advertises a route with metric 100 as E2, every router sees it as metric 100. The internal OSPF cost to reach the ASBR is ignored in path selection. This seems counterintuitive but has a purpose. E1 routes add the internal OSPF cost to the external metric. For example, if the external metric is 100 and your cost to reach the ASBR is 50, your total metric is 150. This provides true end-to-end cost calculation and typically results in better path selection. So when should you use each? E2 is perfect when the external metric is much larger than internal OSPF metrics, such as when redistributing from BGP where metrics can be huge. E1 is ideal when you want accurate end-to-end metrics, especially with multiple ASBRs advertising the same routes. Here's the memory trick. E2 is external metric exclusively, while E1 is external plus internal. In practice, most redistributions use E2 by default, but understanding when to use E1 can significantly improve routing decisions in complex networks. N1 versus N2 routers in NSSA. N1 and N2 routes are the NSSA equivalents of E1 and E2 routes. When you redistribute routes into an NSSA, they become Type 7 LSAs carrying either N1 or N2 routes. The behavior mirrors E1 and E2 exactly, just within the NSSA context. N2 routes, which are the default, maintain a fixed metric within the NSSA, ignoring internal OSPF costs. When the ABR translates these to Type 5 LSAs, they typically become E2 routes. This preserves the original redistribution intent across the area boundary. N1 routes add internal OSPF costs within the NSSA when translated to Type 5 LSAs at the ABR. They usually become E1 routes. This ensures consistent metric calculation whether you are inside or outside the NSSA. The translation process is fascinating. The ABR that performs the Type 7 to Type 5 translation becomes the advertising ASBR for the resulting Type 5 LSA if multiple ABRs can translate. OSPF uses a selection process based on router ID to ensure only one ABR performs the translation. Remember, N1 and N2 only exist within NSSAs. Once translated to Type 5 LSAs, they become E1 or E2 routes. The show IP route output displays N1 and N2 routes differently from E1 and E2, helping you identify which area type you are dealing with. Intra-area versus inter-area routes. Understanding the distinction between intra-area and inter-area routes is fundamental to OSPF operation. These route types have different preferences and characteristics that affect routing decisions. Intra-area routes, O, are learned from Type 1 and Type 2 LSAs within your local area. These are the most preferred routes in OSPF because they represent direct topology information. No information is lost or summarized. You have the complete picture of your local area. Inter-area routes, OIA, come from Type 3 summary LSAs generated by ABRs. These represent networks in other areas. Even if an inter-area route has a lower metric, OSPF prefers intra-area routes. This preference prevents routing loops and ensures consistent behavior. Here is a critical point. When a router is in multiple areas, an ABR, it maintains separate LSDBs for each area. A network might be intra-area in one area, but inter-area when advertised to another area. The same physical network can have different route types depending on your perspective. The command show IP route OSPF clearly marks routes as O intra-area or OIA inter-area. In troubleshooting, always check route types first. If you expect an intra-area route but see inter-area, you might have an area configuration issue. This distinction becomes crucial in complex multi-area designs. Putting it all together. Now let's see how all these concepts work together in a real network. I'll walk you through a practical example that demonstrates every LSA type, area type, and route type we've discussed. This is where theory meets practice. Imagine a company with headquarters in Area 0, branch offices in stub areas, ADMZ in an NSSA, and connections to the Internet and partners. The headquarters routers see all LSA types. They have Type 1 and 2 LSAs for local topology, Type 3 LSAs from branches, Type 4 and 5 LSAs for external routes, and translated Type 7 LSAs from the DMZ. The branch offices in stub areas only see Types 1, 2, and 3 LSAs plus a default route. Their routing tables are small, and updates are minimal. This is perfect for locations with limited router resources. The totally stubby branches are even more streamlined. They just have local routes and a default. The DMZ NSSA blocks external Type 5 LSAs from the Internet. However, it allows local servers to be advertised using Type 7 LSAs. These then get translated to Type 5 at the ABR for the rest of the network. This provides the best of both worlds: protection from external routes while allowing for local origination. This design showcases OSPF's flexibility. Each area type serves a specific purpose. LSAs flow according to rules we can predict, and route types give us granular control over path selection. Understanding these concepts transforms OSPF from mysterious to masterful. Thank you for your attendance. Please consider subscribing to the channel.